Assalamu alaikum. This presentation is on the mechanisms used by the larynx to produce voice. Voice production is essentially an energy conversion process in which the aerodynamics energy supplied by the pressure of the air driven out of the lungs is converted at the glottic level into an acoustic energy by the myoelasticity of the vocal fold tissues. This myoelasticity drives the oscillation of the vocal folds, which essentially modulates the continuous air stream into a series, like a train of air puffs, with a certain rate that is the fundamental frequency of the glottic signals. And this is the essential first part in the voice production. All physical structures can and will vibrate preferentially at its natural frequency. That is a frequency dictated by the physical properties of that object or structure, when the amplitude of the vibration will be maximized much higher than frequencies below or above that specific natural frequency. Anything with a mass will vibrate, be it a playground swing, strings of a piano or a guitar, a pendulum, a bridge, or a larynx. The frequencies, the natural frequencies, will be dictated by physical properties of that structure or that object. And a vibrating object will pick up its natural frequency from a complex excitation frequencies and will vibrate at this particular natural frequency, sometimes with a disastrous effect, like what happened to the Tacoma Bridge when it collapsed after picking up one of the components of the wind and vibrated at its natural frequency to a disastrous end. The motion pattern, the vibration pattern of a system oscillating at its natural frequency, is termed the normal mode or the eigenmode. That's when all parts of that system are moving sinusoidally with that same natural frequency. This natural frequency is described by this formula, in which the frequency would increase with increasing the stiffness of the system of the object, and decrease by increasing its mass, its vibrating mass. The frequencies are dependent on the way the mass and the stiffness are distributed within that structure or that system. In a complex structure or a system with different parts or segments with different eigenfrequencies and different eigenmode of vibration at these frequencies, if this structure is set to vibration, the different segments would vibrate preferentially at their eigenfrequencies. Some of these segments would vibrate in phase with each other, and some would vibrate out of phase. So you had different or several eigenfrequencies and eigenmodes in the same structure. And the outcome, the final outcome, will be a superposition of the independent characters of the vibratory pattern of each of its segments. And that's exactly the case with the vocal folds. Vocal folds are heterogeneous structures with several layers of material with different physical and mechanical properties, including the muscle core and lamina propria with 3 different layers, and the cover, and each of these has a different physical properties. In addition, the muscles of the larynx can change the elasticity and the tension of the vocal folds, and also its geometry, the geometry of the vocal fold, including the length, the depth, the thickness of the contact area, the contact mode itself, that is the vibrating mass of the vocal folds. That's why the vocal folds should be expected to have an infinite number of eigenfrequencies and eigenmodes. The fundamental frequency of the voice during a certain moment will depend primarily on the frequency of the vocal fold eigenmode at this particular moment that we're excited. The eigenmode and frequency in turn depends on the vocal fold geometry, the configuration of the vocal folds, and the length, depth, and thickness of the vibrating mass, together with the stiffness and the stress conditions of the vocal fold. And because these will keep on changing all the time, there will be theoretically a huge number of eigenmodes and frequencies to choose from during voice production. However, it was found out by computer modeling or physical modeling using excised larynges with high-speed cameras that only few dominant eigenmodes, the lowest of the eigenmodes, can actually play a substantial role in the production of voice. Using the computer models or using physical models with larynxes, sometimes canine larynges. This was illustrated well that a combination of only two eigenmodes can capture more than 95% of the variance of the vocal fold vibration in normal phonation and more than 70% of the variance during irregular vocal fold vibration. The two dominant vocal fold eigenmodes during phonation are termed X10 and X11. These are two different modes of motion or vibration. The first one, the X10, presents the lateral to medial oscillation, which is responsible for the opening and closing of the glottis during phonation, and it's actually responsible for the voice production by allowing puffs of air when the glottis opens to pass through it, producing voice. The X11 is another pattern of movement with convergence and divergence of the glottal canal here. You can see that the lower ends of the medial ends of the vocal folds always lead the upper ends during closure and opening of the glottis canal. And this pattern of movement allows the transfer of aerodynamic energy into the vocal fold tissues to support phonation. This is a closer look at what happens during phonation with the self-oscillation of the vocal folds. This diagram describes three different eigenmodes during phonation. We start with the last two because these are the dominant eigenmodes that produces more than 95% of the movement during phonation. This one is the medial lateral type of movement. You could see this thin line is the neutral position, and the vocal folds can move medially, the interrupted line, and laterally, the thick line, and this would allow closure and opening of the glottic canal, allowing puffs of air to pass and phonation to proceed. This is the principal eigenmode or pattern of vibration. The other one is when the lower ends of the vocal fold leads the upper end in movement. So it's a rotational type of movement with the lower end leading, forming a divergent glottis, and also leads it when it is open, forming a convergent glottis. So you could see that the lower end and the upper end of the vocal folds are not in phase during this pattern of vibration. The lower end always precedes the upper end. The third type of motion during phonation is up and down movement, superior to inferior. And there is a considerable argument about whether this is a separate pattern of vibration or actually just a part of these two. As you can see, during these two patterns, there is some leveling up of the upper end of the vocal fold. When the tissues move, there will be some heaping of the tissues in both these modes of vibration, particularly this mode of vibration. It's just a part of the movement that the superior part of the vocal folds will raise up and the inferior part will also raise up during phonation. Or it can be considered a separate type of phonation with an upwards and downwards movement of the vocal folds. Not only the vocal folds has eigenfrequencies and modes, other laryngeal structures can also vibrate at certain frequencies and respond to vibration applied externally, for example through the neck. Below 100 Hz, the vibrations of the ventricular folds are much higher than the vibrations of the vocal folds itself, because the ventricular folds are assumed to have eigen frequencies and modes around 70 Hz. The arytenoids and the aryepiglottic folds can also vibrate at their natural resonance frequency of 50 Hz. And this is the second eigenmode, the eigenmode responsible for changing the glottic canal configuration from a convergent to a divergent configuration. This basically is due to the out of phase movement of the lower and the upper ends of the vocal fold. The lower end would proceed in moving lateral, followed by the upper end, and the same would happen while reversing the movement. The lower end would also leads, followed by the upper end, giving these two types of configuration. These types of configuration helps in transfer of energy from the aerodynamic flow to the vocal folds. As you can see in the convergent configuration, the inlet to the canal is much wider than the exit. According to Brunel phenomena, this would create a higher intraglottic pressure, and this would allow transfer of energy to the vocal folds to open up the canal and allow passage of air. When the configuration is reversed, the inlet to the glottic canal is much narrower than the exit, and according to the same law, this would create a negative pressure inside the canal and allow the pulling up of the ends of the vocal fold to close the vocal folds during the cycle. And this was expected by computer models that show that the thick line here is the intraglottic pressure. This intraglottic pressure is much higher during the convergent part of the cycle than it is during the divergent part of the vibratory cycle. In here, when it is high, it allows the vocal folds to be pushed apart, and when it is low or negative, it allows the vocal folds to be pulled together. Entrainment of the eigenmodes, the mode locking, is a phenomenon that describes how two or three eigenmodes can synchronize together so that their individual pattern of movements can be combined to form a final outcome, much like we have just described of the lateral and medial displacement of the vocal folds combined with the convergence and divergence of the glottal canal at the same time. This phenomena is very much dependent on the airflow through the larynx, on subglottic pressure. If there is very little pressure or no flow, like in vacuum, experimental studies on excised larynges, the vocal folds can start vibration, but its oscillation will damp very quickly and will stop. Under the influence of airflow and subglottic pressure, they will continue to vibrate and may reach a point of self-oscillation when they generate enough energy during their oscillation to sustain the vibration for longer time. This diagram shows the effect of increasing subglottic pressure on two eigenmodes, the eigenmode of lateral and medial displacement of the vocal folds to open up and close the canal, and the other eigenmode of convergence and divergence of the glottic canal during phonation. With increasing subglottic pressure, they reach a point where they can synchronize. Interestingly, this is the point of starting phonation. It corresponds to the minimum subglottic pressure required to initiate phonation. At this point, the combined patterns of movement would have lateral and medial displacement of the glottal canal, and also they have the vertical phase difference between the lower and the upper ends of the glottic canal, giving the convergence and divergence that generates enough energy to sustain the self-oscillation. Adjustments of the vocal folds eigenfrequencies is largely achieved by varying and changing the stiffness and the tension applied on the vocal folds in the antero-posterior direction. This is primarily controlled by activation of the cricothyroid muscle. Frequencies of the vocal folds increases with the increase of either the stiffness of the vocal fold or the stress, the tension applied on the vocal folds during phonation. This describes the relationship between the stress applied on the vocal fold, the force or tension applied on the vocal folds, and the strain, the amount of elongation of the vocal folds under the influence of the force. You would expect an increase in the length of the vocal folds with the increase in the tension of the stress, but this increase is not always linear. In the case of the vocal fold tissues, it's actually non-linear. As you can see, it's like a curve with a considerable change in the length of the vocal fold with only a small changes in the tension in the early parts of the curve, and in the later part of the curve you would need a considerable amount of tension to increase the vocal fold length only a small bit. This property of nonlinear material of the vocal fold explains why in the early parts of this curve, when the vocal folds are only slightly elongated, that the stiffness of the vocal fold is more important than the tension applied. But in the later part of the curve, both the stiffness and the tension or the stress are equally important. Because of the difference in the pace between the inferior and the superior parts of the surface of the medial ends of the adducted vocal fold, when the vocal folds start to open up at the inferior part, it's still closed and maintain closure of the glottis at the upper part. The difference in the pace between the inferior and the superior parts of the surface of the adducted vocal folds is termed vertical phase difference. The vertical phase difference of the vocal folds mucosal wave. And being a non-zero value, it provides asymmetry in the intraglottic air pressure. This is essential for maintaining self-driven oscillation. The phase difference is in turn affected by the vertical thickness of the medial ends of the vocal folds and also by the medial bulge of the inferior part of the medial adducted vocal folds. A similar phase difference is also noted during the conversion and the diversion of the medial ends of the surface of the adducted vocal folds. Much like the phase difference between the superior and the inferior parts of the surface of the medial parts of the vocal folds, the anterior parts of the vocal folds also lead the posterior parts during conversion and diversion, giving rise to what can be seen as a zipper-like closure and opening of the glottic canal. The myoelastic aerodynamics theory proposed by Vandenberg in 1958 still forms our current understanding of how the vocal folds vibrations produce the acoustic vibrations. He also suggested that the mechanism for self-sustaining such oscillation is the Bernoulli's effect. But it's now accepted that several other mechanisms can play a major role in the self-sustaining of the oscillation, and that the Bernoulli effect can actually play only a secondary role. The other two mechanisms that we'll go through in this presentation is first the alternating convergent and divergent glottal canal geometry, and the other one is the inertive properties of the supraglottal air column, the air column from the glottis to the lips. And we shall go through these three possible mechanisms one by one. The condition to have a self-sustained vocal fold vibration is to have asymmetry in the intraglottal canal pressure. The pressure in the intraglottal canal in here. If there is asymmetry providing positive pressure in the opening phase, that would help getting the two vocal folds apart, and negative pressure during the closing phase that will pull the medial ends together to close the glottis. This is the condition for self-sustained vocal fold vibrations. The intraglottal canal pressure equation is here. And as you can see, the intraglottic pressure is dependent on two entities. The first entity is this, and this is the second entity. The first entity is basically the difference between the subglottic and the supraglottic pressure. If there is more pressure in the subglottic area, it's going to drive air through the canal. But this is multiplied by a certain factor reflecting the configuration of the glottis. If you have a convergent glottis, like in the opening phase, with a larger entry, this is A1, the surface area of the entry into the canal, and A2, the surface area of the exit to the canal. If this is the case, this fraction will be smaller than 1, and you will have positive pressure in the canal. If it is the reverse, when you have a larger A2 than A1, then this factor would be negative and you would have negative pressure in the canal. The second entity is the supraglottal vocal tract pressure. So as we can see, the condition for having an asymmetry in the intraglottal canal can be fulfilled by these two mechanisms: the alternating convergent and divergence of the glottis, and the second mechanism is the inertive properties of the supraglottal tract that determines the second entity, and we shall go through these in this presentation. So we start with the Bernoulli effect. This was the initial proposed mechanism for self-sustained oscillation, with repeated cycles of opening and closing of the glottis due to the build-up of pressure when the glottis is closed. Above a certain limit, this pressure is going to drive the vocal folds apart and air would escape, and this would create a stream of air, a jet of air in here with high velocity that is going to create a negative pressure around it, and this would close up the vocal folds again, and a new cycle is going to start with a build-up of the pressure, driving the air after a certain limit of pressure up. This would create the Bernoulli effect again, and the vocal folds would close once more, and a new cycle would again start. But there are now suggestions that the Bernoulli effect is not really necessary for the sustained oscillations, and that it fails to explain some aspects of the vibration cycle of the glottis. Without a vertical phase difference in the medial ends of the vocal fold, the vocal fold surface during opening and closing would be identical. This symmetrical flow pressure inside the intraglottic canal, and there would be a loss of the asymmetry of the intraglottal canal pressure, and consequently a zero transfer of energy from the glottic canal into the vocal folds. And now let's see how this proposed mechanism can actually explain the self-sustained oscillation. Back to the equation of the intraglottal canal pressure, and we see the two entities here that determines the value of the intraglottal pressure. And let's concentrate on the first entity itself, and for now try to neutralize the second entity here by assuming that the pressure in the vocal tract is closer to zero. So this is going to remove this second entity, and also will make the difference between the subglottic and the supraglottic pressure equals only to the subglottic pressure itself. So the equation will now be reduced to this. And let's see how this can provide the asymmetry in the intraglottal pressure during the vibration cycle. So when this equation is applied during the opening phase of the glottis cycle, when the geometry of the glottic canal is convergent with a larger entry area than an exit area, this fraction would be smaller than 1. So this entity would be positive. The positive intraglottic pressure would help in driving the vocal folds apart during the opening phase of the glottic cycle. And the exact opposite would happen during the closing phase of the vibratory cycle, because the configuration would now be divergent with the lower end leading the upper end. And because of this divergence, the area of the exit is larger than the area of the inlet, and this will produce a number here that is more than 1. So this entity would be negative, providing a negative intraglottal pressure. A negative intraglottal pressure in here would help in getting the vocal folds medial ends closer together towards the midline, thereby closing the glottis during the closing phase of the glottic cycle. This graph sums it all. It shows the asymmetry in the intraglottic pressure, resembled here with this thick black line. It is positive in the opening phase of the glottic cycle when the geometry of the glottic canal is convergent, like in here, and it is negative in the closing phase of the glottic cycle when the geometry of the canal is divergent, as in here, and it is zero when the glottic entry is equal to the glottic exit area in here. As you can see, the glottic area entry is shown up here. So this is always more than the glottic exit area in the first half of the cycle in the convergent opening phase. And the reverse happened in the divergent phase. The exit surface area of the canal in here is demonstrated here in this dotted line is always more than the inlet area. So this would summarize the whole findings. The intraglottal pressure is positive during the opening convergent phase, and it is negative during the closing divergent phase. And note that the maximum positive pressure is at the beginning of the cycle, the very beginning of the opening cycle, when an excess pressure is required to push the medial ends of the vocal folds apart, and it's also maximum negative at the end of the closing phase when some negative pressure is required to abruptly close up the glottis. We now move to the other mechanism that was proposed to explain the self-sustained oscillations of the vocal fold. This third mechanism is the mechanism of the inertive, the mass-like properties of the supraglottal air column, the air column above the glottis in here. And as you can see from the previous equation, this is basically the second entity in here, the entity of the pressure in the supraglottal vocal tract. The equation shows that the intraglottal pressure is dependent on two entities, and for now let's try to ignore the first entity that we have been through it with the second mechanism of the convergence and the divergence of the vocal fold canal, and concentrate on the second entity. To do this, let's assume that the inlet area A1 and the exit area A2 of the glottal canal are equal. This will make this fraction equals to 1. 1 minus 1 equals 0, and multiplied by this it will end up as 0 as well. So the intraglottal pressure will depend basically only on the supraglottal vocal tract pressure. So now we need to examine what determine the pressure, the input pressure in the supraglottal vocal tract. It's actually two things in here. The inertia of the air column above the glottis up to the lips, and the rate of the glottal flow, the change in the glottal flow over time in here. That is to say, the glottal flow through the glottis over a time period. The inertance of the vocal tract is in turn calculated from this equation and gives almost a fixed value because it's dependent on the density of the air, the length of the air column in the vocal tract, which is about 17 centimeters or so from the glottis to the lips, and the cross-sectional area of the vocal tract above the glottis, which is about 3.5 centimeters square or so. So this value is almost fixed, and the input pressure into the supraglottal vocal tract is dependent on this, on the change in the glottal flow rate. When the glottal flow increases rapidly, this is going to be increased, and when it decreases rapidly, this is going to decrease. And this would be reflected through the pressure Pi into the Pg, which is now equal to it. Now again, this graph sums it all. It sums up the changes in the intraglottal pressure that is due to the inertance of the vocal tract air column. We have been through a similar graph for the changes of the intraglottal pressure due to the convergence and the divergence of the glottal entry and exit surface area. And as we can see here, the intraglottal pressure is again positive in the opening phase when there is a positive pressure in the intraglottal canal and negative in the divergent and closing phase when the intraglottal canal is below zero, and it reaches a 0 point between the changes in the opening phase and the changes in the closing phase. So we have been through these two mechanisms of convergence, divergence, and the inertia of the supraglottal air column, and to try and explain why the vocal folds can self-sustain oscillations. Back to the equation, we have seen that there are two entities. One of them is the pressure in the supraglottal vocal tract, which is dependent on the inertia and on the change in the glottal flow rate, and the other entity is dependent on the convergence and the divergence of the glottal canal entry and the difference between the subglottis and the supraglottis pressure. So these are the two mechanisms that can explain how the intraglottal pressure have an asymmetry, being positive in the opening phase and negative in the closing phase. Thereby it drives the vocal fold medial ends apart while the glottis is trying to open and suck them together closer to the midline when the glottis is trying to close up. In fact, we have taken the two mechanisms one at a time by trying to neutralize the effect of one side while focusing on the other. But in reality, the two mechanisms would act together to provide the required asymmetry in the intraglottal pressure that is required for self-sustaining the vocal fold oscillations.
By this, we come to the end of this presentation on voice production mechanisms. Assalamu alaikum.